Welcome you all in this new video, and in this video we are going to discuss very important topic of quantum mechanics. Okay, that is particle in a box. Okay, and you are observing the things on the quantum level. Okay, quantum level. So you have to follow all the things, wave function and Schrodinger wave equation. By using the Schrodinger wave equation, we will find the energy of the particle in a box. Okay, at the quantum level. Okay, so this is also a very important concept. Okay, on the basis of this concept you will be able to solve various kind of the numerics, okay, which are based on this particle energy inside a box or free particle which is moving. Okay, so such question will be asked. So let's start our video. Okay, and our video main topic is that energy of a particle. Okay, we have to find the energy of a particle, which kind of the particle, and that particle is moving in one dimensional. Okay, one dimensional. And what is that? That is infinite potential well, and that potential well we observed as a box like this is potential well. Okay, this kind of, and we observe this region as a box. Okay, box region. So let's start our video and derive an expression for energy of a particle in one dimensional infinite potential well. Okay, so what are the conditions that we will follow? What are the steps that we will follow? Okay, first of all we will use the Schrodinger wave equation of wave function, that is time dependent. Okay, by using this equation we will find another solution for it, and when we find the solution there are some constant. Okay, that constant are derived, or we find the value of that constant from boundary conditions. Okay, boundary condition means what are the condition at the boundary of that box. Okay, and then after that we will discuss about the eigen value of energy, means the value of energy that we get. Okay, and the expression that we get. On the basis of that we will find the eigen value of energy. Eigen value of the energy, what will be the energy at n equal to 1, n equal to 2, means at the different stages of quantum. Okay, or quantum number. Okay, so let's start our video. And first of all, consider a particle of mass m. Okay, and is confined to move in one dimensional rectangular box of length l. Okay, what is the concept here? You have a particle, okay, of mass m that is moving in a particular box. Okay, like this is a box. Okay, and this particle is moving inside this box. Okay, and this box is of length l. Let this is our, it's just assumption. Okay, and the particle moves only along a straight line along the x-axis, means if that is one dimensional, it means there is linear motion. Okay, so what is the condition here, and what is the, let this is our box. Okay, let me draw it properly. Sorry, oh, wait a minute. And this is our box. Okay, and this, okay, this is our box, and particle m, mass m, is moving inside it. Okay, and what is, there is another condition that will be, this is the potential value, you can say. Okay, potential well. Okay, so look at here. Okay, what is the length of this box? Have length l. Okay, and there is another condition. Okay, that is the potential inside the box. Okay, potential is 0. Okay, let these are the ranges. Okay, and this is the axis, and this is x-axis. Okay, at this point x equal to 0 and this point x equal to l, that's why the distance between x0 and xl is l. Okay, means length of that particular box. Okay, so in between these 2 points, what is the value of potential? That is 0. And outside these uh, point, okay, what is the value of potential? That is infinite. Okay, means potential is infinite. That's why this kind of structure and this kind of the box, okay, outside, it is called potential well, and we are talking about infinite potential well. Okay, means what is the region between that's infinity? Okay, means the region between the point x0 and xl, means this is the point. Okay, this is the region of length l. Okay, so let's start our video. Sorry, let's do it further. Okay, this is our, wait a minute, this is our box. Okay, and this is x equal to 0 and this is x equal to l. Okay, And what is the distance between these 2 points? That is L, means L is the length of that box, okay, and this is particle M of mass M is moving, okay, and potential inside the box is 0 and potential outside the box is infinite, okay. So what will be the condition? Your potential, okay, because it is very important. We are using this concept when we will derive the expression for energy by using Schrodinger wave equation, okay. Potential V equal to 0 when 0 x lies between 0 and L, and V is equal to infinite when your x is less than or equal to 0 or your x is greater than or equal to L. So these are the two condition and we will apply these condition, okay. So this is the condition, means inside that box the potential is 0, okay. So by using Schrodinger wave equation, okay, and what is the Schrodinger wave equation? That is double differentiation of the wave function with respect to the x square, because x square, why? Because particle is moving along the x direction, okay, that we had considered. It is moving along x axis, okay, plus 2m over h square, okay, E minus V of psi is equal to 0. This is our Schrodinger wave equation, okay. We will solve this equation and derive expression for energy, okay. How? Let's see. So now what is the equation that we have? X square plus 2m E minus V over h square, okay, this is psi and equal to 0. So what is the condition? We have that potential inside that box is 0, okay, inside that box is 0, so this will be 0, okay. So let erase this from here, okay, this is 0, okay, so there is no need to write this here, this is 0, and so this we have, okay. Now place this value, okay, replace this value by k square. Why? That's why we will get a proper differential equation, okay, first order differential equation, that is this. Let k square psi is equal to 0, okay. What is the k square? K square is 2me over h cross square. So this is very important step that we had did, okay. Now by solving this question, this equation, we get the answer psi x. This is the solution, okay. This is, I am putting direct because this is the differential equation and its solution is written like this, okay. A e minus I kx, sorry, plus kx, it is plus I kx plus b e minus I kx. This is the solution of this equation, okay. This is not final solution, this is just a second step towards our goal, okay. What is our goal? To find the energy of particle, okay. So this is the equation that we get as a solution of this equation, okay. Now we will use this equation, okay. How? Let's see. And this is the psi x is equal to a e I k x plus b e minus I k x, okay. A and b are the constant, okay. These are the constant which we have to find from the boundary condition. What is boundary condition means? Boundary condition means at the boundary of this box, okay. What are the condition at the boundary of this box? Okay, x equal to 0. This is, we know that x, when x is equal to 0, it means what? Psi will be equal to 0, okay. So we have to, and when psi is equal to 0, and there is another condition x equal to L, okay, at this condition there will be also psi is equal to 0. So we have to apply these condition here, okay, and these are the boundary condition. So let's apply first boundary condition, okay. First boundary condition, okay. So what is the first boundary condition? When your psi is equal to 0, okay, psi x is equal to 0 and x is equal to 0, by putting these value in this equation, okay, let me change the color. This is the, okay, we have to put the values in this equation, okay. These values, these are the values that we are going to put in this equation. So what our equation will becomes, let this name is equation 1, okay. So what will be get, that is 0 a plus b, and this can be written a equal to minus b, or it can be written b equal to minus a, whatever you want. Okay, so this is the equation or a conclusion that we get. Now applying this, okay, b equal to minus a in this equation. Okay, so when we used to write this, okay, so we get a e I k x minus, because we are putting b as a minus a. Okay, so a is here, a sorry e minus I k, wait a minute, k x. Okay, this is the things that we get. Wait a minute. Now what we will do, by taking a common, okay, what is inside, e I k x, okay, minus e minus I k x. You know, by doing further this equation, wait a minute, okay, we have to solve this question properly, so that's why we will get it and understand very easily. Okay, wait a minute, I'm sorry for this thing. Okay, what was the condition that we have done? Okay, this was the equation that we had already get. Okay, what is the x equal to, a is common, and e I k x minus e minus I k x. Okay, now divide and multiply by 2 iota here. Okay, so this whole term, okay, will be equal to what, sine kx. Now we can write this expression as 2ia sine kx. Okay, this is the expression. Okay, now by applying the second, okay, second boundary condition, and what was the second boundary condition? That was ki psi is equal to 0. Okay, wait a minute, and this was lagging, and this creates too much disturbance. Okay, this is your 0. Okay, and there is also x equal to L. By applying this condition in this expression, okay, so we get, what is the condition, that is psi is equal to 0 and x equal to L. By applying this equation, sorry, this things in the equation, this, okay, that is 2ia sine kx. Okay, so we are going to apply this thing in this expression. Okay, so what will this kind of equation will become, this is 0, okay, is equal to 2ia sine kl, and this will become sine kl equal to 0 and kl is equal to n pi. Okay, and k is equal to n pi over L. So this is the equation that is very important. Okay, now we will square this equation. Okay, we will square the value of k, and when we will square the value of k, then we will get n square pi square over L square. Okay, now remember guys, k is something quantity that we had replaced by something. Okay, look at here. Okay, what is the k square value? K square value is 2me over h cross square. Okay, so we have to replace the value of k square by this value. Okay, so we will get is equal to 2me over h cross square. Okay, from this expression, n square pi square over L square is equal to 2me over h cross square. Okay, from here we can easily calculate the energy. Okay, that is E equal to n square h cross square pi square over 2ml square. Okay, this is energy for En. N is the quantum number, whatever it will be. Okay, so this is the final expression that we have, that is En is equal to n square h cross square pi square over 2ml square. L is what? It is the width or length of that particular box or that region. Okay, it will be already given to you, either you have to derive it, okay, or calculate it. And what is the n? N is the quantum number. M is the mass of that particle which is inside that box. Okay, this is the final expression that we get, and I hope you all understand this, how we derive the expression for energy. Okay, if you like our video, then give a thumbs up. Okay, let's revive all the concept, okay, that we did. First of all, what we did, wait a minute. Okay, yeah, first thing that we did, we use Schrodinger wave equation, okay, for wave function, and then we use boundary condition, okay, which condition at the boundaries means psi equal to 0, x equal to 0, and x equal to L. These kind of the condition that we use. Okay, then we find the eigenvalue of energy. Okay, now understand what we consider. We consider a particle of mass m is moving. Okay, this is already clear to you. Now this is the diagram that you understand. This is the region or box of length L. Okay, these are the values, and potential value is 0 inside the box. Okay, we apply this thing. Okay, this is a Schrodinger wave equation through which we are able to derive the energy. Okay, and this is done. This is the solution for this equation. Okay, and a and b are the constant. We find the value of a and b constant by the boundary condition. Okay, first boundary condition is this, we apply this thing. Okay, and then we apply second boundary condition. Okay, and finally we get the value of k from second boundary condition, and by this value of k we have already a value of k square. Okay, we used to square this value of k, and then we get the value of this. Finally we get the value of energy, okay, of a particle inside a box. So this is the final expression that we get. Okay, I hope you like this video. If you like our video, then give a thumbs up and do subscribe our channel. Thank you so much.